So, uh, so welcome everyone to a new session of our Categorías seminar. Today we have the pleasure and honor of having Eric Rowell from Texas A&M University. He will be talking to us about his work on classification on modular fusion categories. Before starting, if anyone wishes to ask a question during the talk, please unmute yourself or ask the question in the chat. If you don't feel comfortable asking your question in English, please ask in Spanish, and I would be very happy to translate for Eric. Students are especially encouraged to ask questions. Please, Eric, well, take away, and thank you very much.
Okay, yeah, thank you very much for the invitation to speak here. And yes, by all means, ask questions, and probably I can answer and understand it in Spanish if you need me to. So yeah, so I wasn't too sure about the background of everybody, so I prepared this talk. Maybe there will be something in it for everyone, and there will be some things that maybe not everyone is so interested in, but hopefully it'll help. And it's kind of maybe to set some groundwork for other people that might speak later. So right, so this question of classifying modular fusion categories has been something I've been working on for a very long time. And so, and we continue to get new results. So let me dive in here and maybe just give some idea about what a modular fusion category is. And so here I've constructed kind of the family tree of modular categories. And so you can see here, this is the final thing, is the modular category. So how does it work? Well, we start with some kind of just basic category. And then as we go, we'll add some adjectives. And those adjectives will either correspond to some kind of structure, which means there's some choices to be made. If the structure is possible, there may be many. And then there also can be properties, things that we require, but that's not a choice. It's just, it sort of pares down our collection. So I will make these slides available, and I've made it so that if you want to look at a particular definition or kind of the basic idea, you can zoom a little bit like this. And so, right, this is kind of, I won't go through all of them, but I'll just kind of give some ideas. So to start with, we want an additive category, which has to do with kind of the structure of like direct sum. And so that's an actual structure. But then we require it to be abelian, for example. And then we require that to be locally finite. And so all of these things have some important meaning. We actually require that the category have the structure of a linear category, meaning that the Hom spaces are actually vector spaces. And then we keep building this up until we reach sort of modular. So the structures you can see is that it's additive, and then you require it to be abelian, that's a property, locally finite, which just means that some spaces are finite dimensional. You see here. And then we also require it to be semi-simple, which means every object is a direct sum. And then finite, there's finitely many simple objects. And then we can start over here, kind of independently here. We ask the category to be a monoidal category. And then we require it to be rigid, which turns out to not be a structure, but rather a property. And then we add a structure of a braided category. So that's some kind of morphisms between objects. It's kind of like the commutativity of the tensor product. And then we can continue to build. So there's some kind of more technical things like balanced, pivotal. These are structures that one chooses. And then depending on those structures, how they behave, a balanced category can be a ribbon category, some special conditions, a pivotal category. So these are kind of parallel here. A spherical category, that's a property of a pivotal category. And then maybe a couple of important ones is that it would be a fusion category. So the trivial object is simple. So that is required always. And then required to be non-degenerate, which means that if you look at the various bratings between pairs of objects, that this is non-trivial in some sense, except for the case where you start with a monoidal unit. Okay. So I won't dwell too much on all of these adjectives. The point is that you really just build. You add structure, and all of these structures and properties are things that are important and inspired typically by topology, sometimes by physics, sometimes by algebra. So that's just a really brief explanation of what these modular categories are. Okay. I'll give a bit more here. So a modular category over the complex numbers is monoidal, semi-simple, it's linear, it's rigid, braided, it has finite rank. So the number of simple objects is finite up to isomorphism. It's spherical, and it's non-degenerate. And in some ways, all of this is required so that we have a sensible way of describing kind of ribbon diagrams. So invariance of things can be described purely in terms of these morphisms, and each morphism kind of has an associated picture, such as the rigidity has to do with like this cap and cup, and so forth. Okay.
Eric, could you explain a little bit more? So, for example, the last one, not degenerate, is different from your last picture. How do you this about
Yeah, I sure will. So the point is that there are really two ways of, so they're equivalent. So one is to say that the double bratings between objects is sort of usually not trivial. It turns out that's equivalent to saying, okay, we're going to construct a matrix, SAB. And that matrix corresponds to this picture. So it's the invariant of the hot flink, colored by objects in your category A and B. This will give you a complex number. Therefore, for each pair of simple objects, you get, a matrix entry. You put this in a matrix, and the requirement is that this matrix should be invertible. And it can be shown that this very kind of concrete way of just writing down some invariance is equivalent to the requirement that double braiding only gives you the identity if you're braiding with sort of the monoidal unit. So they're equivalent. But we use them both a lot.
Great, thanks.
Yeah, sure.
Okay. I'm sorry, Eric, could you please say a bit more about the fact that rigidity is more a property than a structure?
Yeah, so it's a slightly surprising maybe, but it turns out that essentially that so what you're looking for is if you have an object X, you're looking for another object, which we would call X star, so that certain maps exist, certain morphisms exist, going to the trivial object and going from the trivial object to in the other order, okay? And so it turns out that if you have a dual, it's unique up to unique isomorphism. And so for that reason, it's really a property. There isn't a choice of a dual. And even these maps are essentially unique. So that's why it's actually a property. Yeah.
Okay, thank you very much.
Okay, so anyway, all of these things are very important to us. Being braided, of course. Spherical is a little bit of a tricky thing to explain, but essentially what it does is that you can kind of think of the reason we call it spherical is that if you kind of have this loop going around on a sphere, obviously you can straighten it out, right? And so the requirement of this spherical structure, which actually here I'm describing it through the so-called twist. It's not the actual spherical structure. And we call it a spherical structure, even though it's a pivotal structure that is spherical. This allows us to be able to take traces on morphism spaces, endomorphisms. And so that's how you get all of your invariants, by taking traces of pictures. And the traces basically involve slapping on cups and caps onto some braids. And so then you get something that's really a link, right? The diagram is just a link diagram. And because it's spherical, you get a consistent trace. And therefore, you get a complex number out of it. Okay. Okay, so any other questions on these axioms? I know there are a lot to absorb, maybe.
Just could you say a little bit how the monoidal fusion categories appears in TQFT? Some word.
Sure. Yeah. So the Reshetik and Turayev TQFTs is basically a recipe for starting with a modular category and constructing a 2+1 TQFT. And basically the idea is, well, there's a few ways of thinking about it, but one is that so you have the various axioms of a TQFT, and so like the gluing axiom and the disjoint union axiom, these ones correspond to something like, well, the disjoint union is the tensor product in the category. And so you can kind of think of it in the following way. These objects, for the moment, you can think of them as being like punctures in a disk, let's say. And then you can move them around each other, and that traces out a braid. And then, right, and so this is kind of the structure. Now, the key part, so I'm not going to define TQFT, but maybe the key part of the TQFT that one is interested in is exactly the fusion rules, which I'll describe in a moment. And the fusion rules are what sort of tell you what to assign to a pair of pants labeled by objects in the category. So of course, for any surface, you have your DAP decomposition, disk, annulus, pair of pants. And the key is, well, what's the boundary? How does the boundary information tell you what Hilbert space or vector space you get out? And in this case, it's exactly the fusion rules. And I can even tell you precisely what vector space to assign to a pair of pants. That'll be on another page. So maybe that's kind of the idea. It's the Reshetik and Turayev construction that exactly gives you, modular category gives you a TQFT. And kind of vice versa. Mm-hmm. Yeah, 2+1 TQFT. Okay, so here's some of the invariants and notation that we might need. So the first thing I want to point out is that there are finitely many simple objects up to isomorphism. That's key. And so that gives us, so the number of such things is the rank of the category. Now these fusion rules, these are dimensions of morphism spaces, namely the morphism spaces going from xi, so I think I've got this not quite written quite right. I think what I have actually is this one. I think that's the one I use. It doesn't really matter. But the idea is, look at this thing here. Because this is a linear category, this is a vector space. It's the space of morphisms between xi and xj tensor xk. So this is the vector space associated with a pair of pants whose cuffs are labeled by j and k, and the waist is labeled by I. This is exactly what we assign in the TQFT to that surface. And so the NIJK or NJKI, these encode the dimensions. And we kind of picture them in this way. We can think of it as sort of a trajectory of, like in physics, we call it like a quantum, a quantum trajectory maybe. So time goes up. So the idea is you start with I, and then it sort of splits into J and K in some way. But this is just you can also go the other way. It's totally fine. But these are just the pictures that we use to describe a basis for this space here.
Eric, the subindex has some kind of structure, like a group or something like that, like?
A priori, no. Yeah, so the indices themselves, so like the simple objects, they just form, if you like, they form a ring, even a commutative ring. It's the Grothendieck ring of the category, which is, just it encodes the tensor product rules, basically. Yeah, but in general, it can be anything. This can, lots of different I's can show up in XJ tensor XK. It's totally fine. Yeah. And now, if you start to even just draw these pictures, you'll find that there are things you have to worry about. So in particular, you might have something like this, which would be, a vector in HOM XL to XI tensor XJ tensor XK. And because of the different ways of putting these together, you could also have one that looks like this versus one like this, where, the way you tensor these together matters, right? And so in particular, the spaces where these live are isomorphic vector spaces. And so we need to encode how to change sort of the recoupling theory, if you like how do you kind of rewrite it in this way? And those are encoded in things called the F matrices, sometimes also called 6J symbols. Okay, so that's part of the information of encoding a modular fusion category is exactly these matrices. They happen to be matrices, where the sort of the indices here are related to this mu and the E and the V and the F, nu and the F. So anyway, so this is part of it. And so kind of, if you really want to get a hands-on approach to this, one needs kind of a lot of sort of linear algebra data. Yeah. Now the braiding, this can also be encoded by some matrices. And it's simply, if I were to braid I and J, so that would give me a vector, let's say. So this is supposed to be a vector in some space, a vector that goes sort of from K to I tensor J. And so I, of course, have a basis for those. And I've sort of omitted some of the indices here, but the idea is there's a matrix that tells you how to encode this braiding, just in any of these. Okay, so the idea is the HOM spaces, that's where all the information is being stored. The objects are sort of just almost auxiliary, like in any category, right? The objects aren't so important. The HOM spaces, those are what's key. And so all of these constraints or properties and structures in a modular category can be encoded by a bunch of matrices transforming between the vector spaces of HOMs morphisms. Okay, so now moving on a little bit here. So there's a couple of interesting invariants that we like to use. One is the twist matrix, which is just an encoding of, it's a diagonal matrix that encodes the values of these pictures. Okay, so we don't think of these as being really strings. Instead, we think of them as being like ribbons. So they have a little bit of width. And so when I draw this, this is not the same as just a straight line. There would be some kink in it, some kind of thing. And so it turns out to be a root of unity, which is this scalar here. So that's the twist matrix. And then the S matrix I've already mentioned is the invariance associated with colored Hopf links. And so we have these matrices. That's called the modular data. which is one of the most important invariants we have. Now, you might ask, well, what happens if I take this, if I just take a single loop and kind of close it up, right? You can certainly do that. This is already over here. If you take J to be the trivial object or the monoidal unit, these numbers actually show up here already. This would be for J equal, the trivial object or whatever. And so you get these dimensions. We call them quantum dimensions or categorical dimensions, and they behave just like dimensions, except that they aren't integers. Okay. I see a hand up. Maybe Eduardo has a question.
Yeah.
Yes, thank you. Yes. Sorry, thank you. In the S matrix, what is the meaning of the color of the link in the entries of the S matrix?
Yeah. So very good question. So the idea is I'm just the color really I'm just trying to use to indicate that I and J are different objects. So the particular color isn't important. I mean, the red and the green. But the point is that each of these things can be chosen to be colored by a different object in the category. Okay. So
okay, then it's just to specify that there is two kind of objects. That's all.
Yeah,
okay.
That's right. Yeah, not the same.
Okay.
Yeah, that's right.
Yeah, thank you. Thank you very much.
Sure thing. Yeah. Okay, so more invariants. So an important invariant of the category is if you just take the sum of the squares of all the simple objects, then this gives you something we call the categorical dimension of the category. Yeah. And this is pretty important. Anyway, it's kind of a measure of how big the category is in some sense. And it's the reason we take the sum of the squares is it's related to the fact that if you take a finite group and you take the sum of the squares of the dimensions of the irreducible representations, then you always get the order of the group. So this is kind of an analog to the order of a group. Now there's another kind of dimension which may or may not be the same, which you can get in the following way. Remember, I defined these nijks. Well, you can take these nijks and also form matrices just by fixing one of the indices. And these are what we call the fusion matrices. So they have entries that are exactly these fusion coefficients. So fix I maybe, and then take the entries. Let J and K run over all of the simple objects. Then you get a matrix. And this matrix, of course, has non-negative integer entries. And so in particular, you can, you can look at the eigenvalues of that matrix. Turns out the eigenvalues, they're algebraic integers for sure. But the largest one is always going to be a real number, largest in modulus. That's by the Perron-Frobenius theorem. And so we can define the FP dimension, the Frobenius-Perron dimension of an object to be just the largest eigenvalue. Okay. And amazingly, this also behaves just like a dimension in the sense that if you take a product of the dimensions, it will equal the sum of the dimensions of the constituent parts when you decompose it, this tensor product. So they're both quite useful. Okay. So let me give an example, a non-trivial example, and just kind of work through this. Okay. I don't have any agenda here, so I don't care if I finish this talk at all. So this is called the Fibonacci category. Okay. It has exactly two isomorphism classes of simple objects. The monoidal unit, always have that one, and one other one, which we call tau. Okay. Now, tau is self-dual, meaning that it is isomorphic to its dual object. Okay. So that kind of has to be. And so I can write down all of the fusion rules, all the fusion coefficients here that I need. and they're either 0 or 1. Most of the time, I guess, they're 0. In these various cases, you get 1. These are the only ones. And so you can kind of think of it in a sort of topological way as well. Here is the space Hom tau to tau tensored with itself. Okay, that's a one-dimensional space. The reason is, look, this is 1. Okay, and you can think of it as being the vector space associated with a pair of pants where all 3 of the labels are 1. Okay, which is sort of this one here, just the index. And you can also look at Hom from the trivial object, monoidal unit, to 2 copies of tau. This is the picture we would look at here. And the reason that there's no circle here is anytime you have a boundary component or an object labeled by the monoidal unit, because it's the monoidal unit, you can just ignore it, essentially. You can sort of delete the object labeled by 0, because it's, in physics, we say it's because it's the vacuum. You tensor with the vacuum, nothing happens. But anyway, in sort of the algebraic point of view is just that when you tensor with the trivial object, nothing happens. And so here, this is also one-dimensional. It's spanned in this way, just to give you some pictures. And we have complete information here. You can just go through and you can actually just solve by hand, essentially, all of the requirements. And so this is one solution. So we have this F matrix. And so it's labeled by, so it's a matrix. So you have X and Y, and it's really just the label here is all you need. Okay. And right, and so you get one matrix that's actually 2 by 2. That's the only kind of relatively interesting one. And it looks exactly like this, where here this phi is the golden mean. So that tells us how to resolve the different ways of tensoring these objects together. There's really only one non-trivial one, but this gives you everything you need to know. The categorical dimension of this object here is the golden mean, and that coincides in this case with the FP dimension. Now the braidings, so if I want to braid in this way, I have a matrix R, and I can write down exactly what these are. So in this case, they're all 1 by 1, not much happening. But you can see here that they happen to be roots of unity, 5th roots of unity. Or maybe here that's a 10th root of unity. The twist, there's only one twist that we have to think about. The twist on the trivial object is always 1. And so we have this value here. Okay. So with this information, you can just, if you had for example, a quantum computer that was based on the Fibonacci theory, this right here, this is all the information you would need in order to kind of do calculations. Same thing if you wanted to compute invariance. You can just do any invariant you want using this information. Okay. So any questions on this example? It's kind of the smallest one that's interesting, right? As objects, their dimension's not an integer. And again, you don't need to know all of the details of this, but it's a nice example. Okay, so let me move on and tell you a few ways to construct modular categories. So again, I'm going to be a bit impressionistic. By all means, stop me. I'm glad to say more. So maybe the most ubiquitous place in which these modular categories show up are from quantum groups. So I'll just sort of say, you start with, say, a simple Lie algebra, G. You look at its universal enveloping algebra, UG. Okay, that's a nice Hopf algebra. You can deform that Hopf algebra, a Q deformation, to get something we would call probably the Drinfeld-Jimbo quantum groups. And now you can look at that. So that's some kind of Hopf algebra, quasi-Hopf algebra maybe. You can look at its representation category. Okay. And so that's something interesting to do. And you get, well, some kind of actually a ribbon category. And well, if you specialize your parameter Q to be a root of unity, then interesting things happen. This category is not semi-simple. It doesn't have finitely many simple objects. But those are the two main ways in which it fails to be a modular category. But it turns out you can take a quotient of this category by some tensor ideal, just like algebra construction, and you wind up with a nice category, which very often is modular. It's definitely semi-simple. It has finitely many simple objects, and it retains all of the nice properties that rep UQG also had. Okay. So an example. So I'll use sort of the Kac-Moody style of notation. SO5 level 2. Okay, this corresponds to taking G to be, well, SO5, and you take Q to be, well, a 20th root of unity. Looks like this. L is 10. When you do this process, what happens is, well, it turns out that the representations of UQG look an awful lot like the representations of G, at least combinatorially. When you take this quotient, the effect is to cut. Well, it's really, the cut's really here. You sort of take the fundamental Weyl chamber and you truncate it, you cut it. And so now there's only finitely many simple objects, in this case, 5 of them. Okay. And all of kind of the interesting things that we had from the quantum group are retained. So we know how to take tensor products because we know how to do it in the category, in the larger category here. And so anyway, this is an interesting one. So we get in particular this nice rank 5 category. So it has 5 simple objects. It has some objects of dimension square root of 5. Okay, so that's one huge class. The main class of examples of modular categories are constructed in this way. So you might ask what invariants or what TQFTs show up. So these are somehow related to like the Chern-Simons theories often. Okay, so it's a very ubiquitous, very important example. Another set of examples come from just finite abelian groups. So you start with a finite abelian group and a non-degenerate quadratic form on that group, Q. Then you can construct a modular category whose objects are really just the elements of the group. And the tensor product is just like the multiplication in the group. Okay, so in this case, the simples are all invertible in the sense that you can find something to tensor it with to get the monoidal unit out. So in this sense, the simple objects really do form a group in this sense. But since this form is non-degenerate, it turns out that this is actually a modular category. Okay, the non-degeneracy of the quadratic form gives you non-degeneracy of the S matrix. And here, the morphism spaces are usually, well, they're one-dimensional or zero-dimensional. And the twists are given exactly by just the value at the quadratic form. It's a very simple kind of construction, but quite useful. So these are called metric groups. So the invariants are probably not very rich in this case, but sort of toy models and used in other constructions very often. Okay. So those are a couple of sort of in nature constructions. And here's an important theorem. It turns out that if you have any modular fusion category so that every simple object is invertible, we call that pointed, then it must be of this form. So that actually gives a classification already of so-called pointed modular fusion categories. So I just give a couple of examples quickly. So take any prime P. I can define a quadratic form Q sub J given by its value at A is just this root of unity. Depends on J, and there's an A squared in there. So that's for an odd prime. You can also get them for the prime 2. So this, there isn't much happening for this quadratic form. All you need to know is where one goes, and it goes to I. And this is an important theory in physics called the semyon theory. Okay, so let me give you a few more ideas about how to get new ones from old ones. I might skip some of these examples because some of them are a lot of technical details, and maybe we don't have too much time. But here's an obvious thing you can do. If you have two modular fusion categories, you can take their sort of just direct product, basically. That gives you a new category. So, and if they were modular to start with, the product will be modular. Fundamental construction. And it turns out that there's kind of a converse in some sense. If you happen to have a modular fusion category sitting inside another modular fusion category, then the bigger one automatically factors as a product of modular categories. Okay. It isn't necessarily a unique factorization, but there is a factorization. You can break them apart. Okay. So another construction that's kind of interesting and important is called boson condensation. And here, what we do is the following. If you have a finite group G, then its representation category forms a braided fusion category, definitely not modular, but rather it's symmetric, which is kind of the opposite of modular. Because look, in this case, if you double braid any pair of objects, you always get the identity. Okay. So that's a braided fusion category rep G. And there's just an aside to remember that in a modular category, this never happens, essentially. So it's the opposite end. Now, if you have a category that is equivalent as a braided fusion category to rep G for some finite group G, we call it Tanakian. And we also sometimes call it a bosonic category. There's also fermionic ones, but we won't go into those. So what can you do? Well, if you have a Tanakian subcategory of a modular fusion category, then you can do something called boson condensation, also called de-equivariantization. Maybe that's a more appropriate word for this seminar. But the idea is that essentially you take this collection rep G, or this thing that looks like rep G, and you condense it down to nothing, down to the trivial object. So you get a new category out of this, kind of like a quotient in some sense. So it's a category that has the same objects, but more morphisms, different morphisms. So in particular, you take an object in the category C that looks like, well, it's the functions on G. That will be an object, given that you have this here. And so, and then you define new morphisms between X and Y in this new category as, well, you put on an A, okay? And that's in C. So you just change the morphisms a little bit, and it gives you this kind of quotient. And it creates quite a beautiful category. The new category will be G graded, meaning it has a direct sum decomposition into subcategories, so that when you tensor grade G with grade H, it lands in grade GH. And once you've done this, if you take, so this is for all elements of the group G, this will be a faithful grading. And if you take G equal to the identity in G, so this one, this will again be a modular fusion category. And that's what we call the boson condensation. Let's see. So this is a construction from some modular category to get a new modular category. An example of this is you can take the twisted double of a finite group, look at its representation category. this will always contain the representations of G. And if you condense it, you'll get down to really a trivial category, just the rank 1 modular category of vector spaces. Let me skip over symmetry gauging. Maybe someone will talk about that. But it's kind of a sort of the other direction to boson condensation. Let me briefly say that there's a construction that we call braided zesting, where you can construct a new category. Here, you have an abelian group A, and you have a modular category that is A graded. And well, you also have another group B and some potentially, well, a symmetric subcategory that sits inside the trivial component and is pointed, so some extra conditions. So basically you kind of like have, it's graded by A, and then you also have a copy of the group B kind of sitting inside in some sense. It's pointed, so it means it's an abelian group in particular. And then you can have these various constructions. So you start with a 2-co-cycle. You can construct new fusion rules. You change the fusion rules by tensoring with an invertible object. And then you need to sort of correct the problems that arise because of the associativity. So to correct associativity, you then take this 3-co chain. The braiding gets adjusted. The twists get adjusted. And often the result is a modular fusion category again. Now, I won't go into too many details here. Julia Plavnik, I think in some weeks, will give a talk, I think dedicated almost exclusively to braided zesting. So maybe just a preview of what she'll say. Okay, so I'm almost out of time, but let me just mention that, so I should stop in 5 minutes, is that right?
Yeah, you can take also 10 minutes, I think.
Okay, yeah, we started a little late. Yeah, that's true. Okay, thanks. So here's the project that I've been working on since maybe, I don't know, 2003. So this was a question that I was asked by Zhenghong Wang, is how to classify modular categories by rank, just move up ranks. And so it turns out that this is it's a feasible problem. It's a difficult one, but one can work on it. A lot like, trying to classify finite groups, maybe finite simple groups. So what happens is, so we want to try to understand all of the modular categories of a given rank. So the first thing that really helps is something called Oakniana rigidity, which says that once you've nailed down the fusion rules, these NIJKs, there are at most finitely many braided fusion categories with those fusion rules. Okay, so that cuts it down to a finite problem if you can nail down the fusion rules. Okay. Now, you don't have to worry about the next step, which would be to put a sort of a spherical pivotal structure on there, because there's only finitely many possible choices. So to add on here, there's only going to be finitely many. Now, fortunately, so these fusion rules, you can extract them from your S matrix. So what that means is the S matrix, so this weird complex matrix that we got by taking traces of things, it actually determines the fusion rules by this Verlinde formula. So that means that if we wanted to classify all modular categories of a given rank, it would be enough up to finitely many, a finite amount of ambiguity perhaps, to classify the modular data, namely the S and the T matrix. Okay. So there's a lot of tools that we have to use here. It turns out that all of the entries of the S matrix, all of the entries of the T matrix live in nice, in fact, abelian extensions of the rationals. So you can use Galois theory. You've got lots of matrices lying around, and so you can do some matrix analysis. Also, perhaps the most crucial thing is that the modular data isn't just a couple of matrices. It turns out that they give you a projective representation of the modular group, hence the name. The modular group being SL2Z. These arise as the mapping class group of the torus, which sort of shows up in this setup. And so this S and T matrix have a lot of constraints. It's a very interesting collection of constraints. Here I give you a bunch of them, okay? And they're a little bit hard to just, digest looking at them. But the point is, it's lots of polynomial constraints. And even more than polynomial constraints, they're sort of number theoretic constraints. The last one is the one that was most important recently in proving that for any given rank, there are definitely finitely many modular categories, the rank finiteness theorem. That relied on this so-called Cauchy theorem, which is analogous to the Cauchy theorem of finite group theory. Basically, it's saying that the prime divisors of D squared, so prime ideal divisors, and N, which is the order of the T matrix, okay, it's a finite number, coincide in this Dedekind domain. So there's some heavy number theoretic constraints on here. There's representation theoretic constraints. So it's a really well constrained problem. And anyway, one can make some progress. So let me see how I should do this. Well, maybe I should stop here and ask if there's any questions here.
Thank you very much, Eric.
Thanks.
Is there any question? Just raise your hand. Well, I have two questions. Maybe it's one is about this name of modular that I think it comes from the modular group. So how, in essence, is associated to TQFT is related with the modular group?
Yeah. So it turns out that if you have C, a modular fusion category, and you have any surface, maybe sigma, and it can have boundary. So let's say sigma in G, genus and N, okay? Then it turns out, so if you have such a thing, the TQFT will give you a vector space associated with this thing, right? And I kind of explained a little bit of how to do that. Maybe I should have said more, okay? And so this is a vector space. Now, it turns out that the mapping class group of this surface will act on this vector space. Okay? This is for any surface. So for example, here's a surface, just a disk with punctures. And you should, I should be a bit careful. I didn't, I'm leaving off some information. Of course, there's labels for, the end, there's some labels here of simple objects, but maybe, maybe we do the same object for all of these things. And then maybe the outer one, we just label by the trivial. So it's really, if you like, a punctured sphere. And so the mapping class group, right, of this sort of picture is in this case, something like the braid group on 4 strands. Or, it's not exactly, but something like that. Okay. And so the braid group shows up as a mapping class group action on the Hilbert space that shows up from the TQFT. And then it turns out that if you take the torus, okay, then the vector space associated with this will be, it'll have dimension exactly sort of R, that this is the rank. It's actually, you just use, in fact, you can prove that just using the gluing and disjoint union axiom, maybe even just gluing. Gluing axiom will tell that to you. And so in particular, right, that just tells you the space. It turns out S and T give you the action. Here S, you know, and you know how these, like T acts by like a Dane twist, and S is some kind of, you know, the other thing. Yeah, yeah, the flip. Yeah,
the flip. Yeah. Okay.
Yeah.
Okay. And well, just two last questions. It's because of this condensation and testing. So there's some process in when we construct 1 + 1 TQFT that we associate Frobenius algebra, and we have that G Frobenius algebra is a G TQFT. So when you make, there's something called orbifoldization, yeah? that you take a G Frobenius algebra and then you have some Frobenius algebra. Is this kind of similar, or is the categorification of the condensation process?
Yes. So yeah, certainly there are. Yeah. So I don't remember precisely what the orbifolds are, but I think in this case, indeed, orbifolds should be something like condensation. I might have it not quite right. There's a number of things. So there's the coset construction. There's orbifolds. There's these things that come from conformal field theory. And if it's the same notion for me and you, I think that's right. I think it's an orbifold.
Yeah, also when you make the orbifoldization, for example, if you have a cohomology theory associated to an orbifold, then you will have something that is just a Frobenius algebra. It's an invariant for the orbifold. Yeah.
Okay. Yeah. Yeah. It sounds likely.
And well, the last question is just about the testing. Is this quite similar with discrete torsion? For example, you have a G Frobenius algebra, then you take a 2 cocycle, and then you associate another G Frobenius algebra with a different product. So it's also the categorification.
I suspect it is. So ours is a little bit more like internal to the category, but recently we were able to show that there is some kind of thing where you take two things, you sort of put them together, and it's much like this sort of, yeah, you're sort of pushing one of these categories around by another one, which I think is kind of like this sort of torsion. Maybe, at least in philosophy, it's similar. Yeah, yeah. Let's see, I think there's another. Maybe Juan had a question.
Juan has another question.
Yeah, thank you. Well, thank you very much for the talk, Eric. I have a couple of very basic questions, maybe. So, well, first of all, so from a modular fusion category, you get a 2 + 1 TQFT. From a 2 + 1 TQFT, can you decide if you get the TQFT from a modular fusion category?
Yeah, so there are some ideas. Now there's some extra words that you might have to throw in, like it might need to be a 3-2-1.
Okay.
So not fully extended, but at least partially extended, I think. Then in this case, you can recover a modular category that does it. This is in a series of papers by I think Douglas and maybe Vickeray, Bartlett, I think, is on that paper. Anyway, there's a series of papers where this is exactly what they were trying to do. Start with a TQFT and construct it. Now there's kind of a philosophy. The idea really is that whatever is assigned to the point is supposed to be a modular category, right? If it's fully extended.
Yeah.
But even if it's not, maybe there's something one can do. Yeah.
Okay. And well, I suppose that's and the reconstruction of the if you have your extended 2 + 1, 2 + 1, well, 3, 2, well, your extended TQFT,
yeah,
and you get your modular fusion category, that's not, I suppose, unique in any sense.
Right. So, yeah, there probably is some amount of freedom, but maybe in this particular case, they could be at least pretty close to being equivalent. I mean, there's a different thing, which is the Tarai-Vero construction. And that starts with a fusion category, a spherical fusion category. But really what it's doing is it's sort of constructing a modular category in some sense first by taking the Drinfeld center.
Yeah.
And in that case, then things can be non-equivalent, but they'll be Morita equivalent. So there is this notion of equivalence. But that's the Tarai-Vero. I've been talking just about Reshetik and Turayev. Yeah.
Okay. Okay. Yeah. Thank you. Well, just another even more basic question about the Verlinde formula. So it involves the terms of the S matrix and the invariance associated to colored pairs of bands. And so, how can you explain that? Well, could you just say a bit more about it, just geometrically?
About this thing. Yeah. So okay. So maybe the way to think about it really is that the S matrix, one can show that it diagonalizes all of the fusion matrices simultaneously.
Okay.
So to me, that's really more of an algebraic fact. And it has to do with basically on the objects, there's two products. There's the product we're used to, and then there's a convolution product. And so in some sense, it's interpolating between those two. And so that's that's maybe the more key thing. It diagonalizes these things.
Okay.
I haven't thought too carefully about like a geometric reason for this. So it's kind of like, dimensions of pairs of pants is somehow related to this sort of somewhat complicated sum. But you can rearrange it to just really be the same thing as, this diagonal matrix of dimensions.
Okay.
Is equal to a conjugation of the, by the S matrix of the fusion matrices. Yeah.
Okay. Yeah, I think that's, I've seen it quite a few times. And I think it's very beautiful. I've never really understood it geometrically. It seems somewhat magic, I don't know, a bit of magic and some intuition that I don't get. But I think that, that explanation is it's a pretty big step forward. Thank you.
Yeah, sure. Yeah, thanks.
And well, just a final question, just even more basic than that. Why is the modular data for modular fusion category just intuitively the important thing? Like you start with your modular fusion category, you can draw all these drawings, decorated drawings. And I mean, one thing that you obviously would find important would be the dimensions. And of course, you would think, okay, the decorated hop links are something interesting, of course. But I mean, just if you just come at it just geometrically, why would you just think, okay, the matrix formed by the hop links, why is this so important that determines the fusion category up to finite choices and so on and so forth?
Right. Yeah. Well, and actually, so I should say that the T matrix is you can from this as well. So this this is always equal to the dimension times the twist.
Yeah.
Right. So this is really some kind of framing question, right? If you like.
Okay.
So it's sort of the invariant of, it's ribbon invariant. So in some sense, these are sort of the simplest ones maybe that you can conceive of. Now, I should say that we had a conjecture that was proved wrong, that the S and the T matrices should actually determine the category completely.
Okay.
It's not true. So it turns out that there are modular categories that have the exact same S and T matrices, but they're inequivalent, even as like fusion categories.
Okay.
And so Colleen Delaney, she's coined the term modular isotopes for these. So to actually really determine, that's an open question. Like what other links and knots should you include, right, in your data to determine the category? And maybe the guess is that there should be finitely many. So far, it's true, but we really don't know very many examples. The smallest rank example we know of two categories with the same S&T matrices, but that are not equivalent, is in rank 49.
Oh, wow, that's pretty good.
Yeah, it's huge. I mean, there should be one before that, but we don't know. It turns out that they're related by zesting.
Okay.
So they are related in kind of a very explicit way, maybe a subtle way, but explicit. Yeah. So this is, I would say that that's a very good question, and we're all thinking about it. I think Colleen probably has thought about it much more than I have about this kind of question, like why these things. Yeah. But it's it's a great question. Yeah,
I suppose the idea that they're the simplest possible ones that you should consider is that's good enough for me. So just very quickly, I'm sorry if I'm keeping you here. So do you guys have any intuition as to which other links you would use to just determine your category?
Yeah, so it turns, well, at least for us, the Whitehead link was quite useful. For some other people that did something similar, they used the Borromean rings, right?
Okay.
And those both are sort of linking number strange cases, right? So that's maybe the intuition. Maybe I think there's maybe some cases where like some 5 crossing knots could also be useful. Again, Colleen and Alan Tran did this whole computer search to see which ones were most useful. And they have this big list of, like, what links are useful and which ones are not. So but Whitehead link maybe is the next one.
Okay. Well, thank you very much, Eric, and thank you for the talk and for answering our questions.
Sure. Yeah, no problem. Yeah, thanks for inviting me. Yeah, look forward to meeting you all in person.
Yeah, thank you very much, Eric. So I think there are no another question of the public.